All right. Start the recording and let's begin. Okay. So, we got two sections to cover today. We've got to cover random variables and we've got to cover expectation or expected values is what I'm going to say. I'm never going to say expectation. We'll start with random variables. Now, I begged you guys to read this section ahead of time, so I know you all did that, and we could almost skip it, but we'll just cover it just for the fun of it. Right? Yeah, good plan. Okay, random variable. So, start out with a sample space, SP. We all remember what a sample space is, right?
Yeah.
S is just a finite set of, doesn't matter. P is just a probability function. It assigns a probability to everything in S, and those probabilities add up to 1. There's no such thing as negative probabilities, etc. You're getting used to those. So we've got a sample space and let V be any set. Anything. Doesn't matter. It's just a set. Then a function x, that's a function. This isn't a number, it's a function. A function x whose domain is our set of outcomes. Doesn't matter what the image is, any set. A function whose domain is S is called a random variable. It's just a function whose domain is S. The image can be anything. Now, usually, we are interested in random variables whose image is real numbers. Those are called real random variables. So this is a random variable. If V is equal to a set of all real numbers, then a function from S to R is a real random variable. So random variable, just a function whose domain is S. A real random variable whose function is domain is S and whose codomain is R. That's it. Pretty simple definitions.
Mm-hmm.
When you have a sample space, there is no right random variable. There's just useful versus not useful. The same way that we could have come up with any probability function we wanted, as long as it followed a couple rules, we can come up with any random variables we want, as long as the domain is this. It's a random variable. So there is no right random variable for a sample space. You pick one that you think is useful, and you see things about it. So let's jump into this. Pair of dice. So we're used to the pair of dice sample space, right? Where we let S be the set of all ordered pairs, where the left-hand thing is what the first die shows, and the right-hand thing is what the second die shows. And we're going to assume that these are fair dice, so the probability of any particular outcome is just 1 over 36. You with me so far?
Yes.
So I'm going to come up with two random variables. These are going to be real random variables, but they're random variables. One we've already been working with, the other one's just to see a contrast. So my first random variable gives me, if you give it the ordered pair AB, remember, its inputs come from here. Pick one of these inputs, that's AB. What does X spit out? It spits out their sum. So in other words, what does X give me? It gives me what you typically mean when you say what you rolled with the dice. If I take it and I roll it, and I roll a 2 and a 5, you say I rolled a 7. You good with X?
Yes.
Okay. Y is just another random variable, one that you're not as used to. We're going to say give us the product of the dice. If you roll a 2 and a 5, that's the same thing as a 10. Good?
Yes.
Okay. So let's make sure. X of 6 and 2 is 8. Y of 6 and 2 is 12. X of 7, oh. Okay, now we're jumping. Now, so you're used to using the random variable. Now we talk about the probability that the random variable gives us a certain output. That's what this is. The probability that the random variable gives us a certain output. In general, I can't believe I didn't write this as a definition. The probability that X is equal to A is equal to the sum of all S in S how would I say that? Well, we'll come back and write the definition explicitly. Let's not confuse you. Well, I think I got it. So when I say the probability that X is equal to 7, that means the probability that the random variable spits out a 7. What's the probability that my random variable spits out a 7? 1/6. 1/6 of my rules do the sum. On 1/6 of my rules, the sum of the dice is 7. x is the sum of my dice. 1/6 of the time they give me a 7, right?
Why is it 1/6?
How many ways can you roll a 7? A 1 and a 6, a 2 and a 5, a 3 and a 4, 4 and a 3.
Okay.
Yep. Okay. Let's keep that over though. That is equal to 1/6. Okay, now with our random variable y, what's the probability that y gives us 10? How many ways can I roll 2 dice and have their product be 10?
2.
2. I can roll a 2 and a 5, and a 5 and a 2. Those are the only ways. So 2 out of 36 is the same as 1 out of 18, right?
Mm-hmm.
Alright, let's do another one. What's the probability that x is 8? 5/36. There are 5 ways I can roll an 8 when I roll 2 dice. 4 and a 1, 3 and a 2. 4 and a 1, 3 and a 2, 2 and a 3. Wait, what am I rolling?
Yeah.
I got completely mixed up in my head. Roll an 8. When we're rolling an 8, that's a 6 and a 2, a 5 and a 3, a 4 and a 4, a 3 and a 5, a 2 and a 6. I switched to 5 in my head for some reason. Oh, so I writing 5. That's fine. And then what's the probability that the product of my rules is a 12?
1.
4/36.
Yeah.
4?
How would you do that with the times?
How many ways can I roll 2 dice and have their product be 12?
1, 2. 2 times.
What are they?
1, 2, and 6.
2 and 6 words,
3 and 4.
and 3 and 4, and 4 and 3, and 6 and 2.
Oh, yeah.
So there's 4 of them.
Yeah.
So 4 out of 36, or 1/9, right?
Yeah.
Okay, so that's working with random variables. So now, let's do some more. Tossing a fair coin 8 times, and we'll set up our sample space. I'll just let S be all the possible ways that we can write out H's and T's in a list of 8. With me?
Yeah.
Okay. So what is the probability of a particular outcome?
1/2 to the power of 8.
1/2 to the 8,
Yeah.
right?
How did you do?
What's the size of S? How many things do I have in here? A lot. 2 to the 8 is a lot.
Oh, it's 2 to the 8. Why is it 2 to the 8? Now I understand. But why
I
is
need
it-
to choose, for a particular flip, I have 2 options for the first one, heads or tails, 2 for the second, 2 for the third, 2 for the fourth, 5th, 6th, 7th, 8th. 2 to 2 to 2 to 2 to 2. 2 times 2, 8 times is 2 to the 8.
And the probability is 1 over that.
And we're saying that the probability of one of those outcomes is 1/2 to the 8. 1 over the size of S is the way that we've been writing that, right?
Okay, yeah.
Okay. So, we're going to create 2 random variables now. One random variable, x sub h, gives me the number of heads in a flip. And another random variable, x sub t, gives me the number of tails in a flip. So, x sub h, when I plug in this string, spits out a what? 3, right?
Yeah.
And x sub t, when I plug in the same flip, gives me a what?
5.
You sure you counted them all?
Yeah.
5. Yeah. Now, so far we've just been using real random variables. Let's come up with another random variable, z. What does z do? It gives me the position of the heads. So I can create a random variable z that gives me the position of the head, so when you give it that same string, it spits out a 1, a 2, and a 5 in a set. Perfectly fine random variable. I'm just coming up with a bunch of random variables for the exact same sample space. Just to show you, there's a variety. They don't have to be to the real numbers. We just usually like them to be to the real numbers because then we can calculate their expected values, which we'll do next. Okay, so let's do some more. Continuing what we were doing. So now, what's the probability that x sub h is equal to 4? What's the probability that when I flip a coin 8 times, 4 and exactly 4 of them come up heads?
8 choose 4.
8 choose 4. Nice. Let's make that a little closer. Everyone understand how she got 8, choose 4?
Yeah.
There's 8 positions. We need to choose 4 of them to be heads. How many ways can you choose 4 of 8 things? 8 choose 4. Does that one make sense? Any questions on that? Good?
Mm-hmm.
Okay. What's the probability that we have 5 tails?
8 choose 5.
8 choose 5. Nice. Oh, almost. We're looking for the probability. That's how many ways we get exactly 4 heads. We need the probability. Sorry. So come back. It's 8 choose 4 is the number of ways that we can do it, but how many ways total? Can I get my flips?
2 to the power of
2 to the 8. Because yeah, this definitely can't be more than 1, right? Sanity check, we're talking about probabilities. Probabilities can't be more than 1. Okay, so 8 choose 4 over 2 to the 8. There we go. And now, what's the probability of me getting a 5?
8 choose 5 over 2 to the 8.
Yeah, 8 choose 5 times 1 over 2 to the 8. There's another way that we can do it. The number of ways I get it times the probability of each one of those ways. Does that make sense? Are we getting confused by anything?
Okay, wait a sec. Can we just take a step back for a minute and go to the Z, like the position of heads thing? What?
We're not going to do anything with that. I'm just saying it's a random variable.
Okay, but like, why did you do the Z and then all A's and T's equals 1 to 5?
I'm just saying I can create a random variable like this. Z gives me the position of heads. So if you give Z this string, it spits out the set 1, 2, 5. Notice all our other random variables were spitting out numbers, spitting out number. I created a random variable that spit out a set.
Why is it splitting at 1 to 5?
There's a heads in the 1's position, the 2 position, not the 3, not the 4, but the 5.
Oh, okay.
Okay,
Okay.
yeah. So Z was just showing you a different kind of random variable, and we're done with Z after this. Make sense?
Yes.
Any other questions? Okay. So, let's look at a more complicated one. Let's say I want the probability that the number of heads I flip is greater than or equal to 3, and that the number of tails I flip is greater than or equal to 3. Oh, geez.
That's
getting
easy.
hard.
That's easy.
Now notice that this is the exact same thing as the number of heads I have being greater than or equal to 3, and the number of heads I have being less than or equal to 5, right?
It is.
Yeah, if I have 5 heads, I have 3 tails. If I have 4 heads, I have 4 tails, etc. So do you see how these two are the same thing?
Yeah.
Anyone confused by that?
Oh.
Not confused? Okay, so what's the probability?
Wait.
Okay, so I think it's 3 choose 8 plus 4 choose 8 plus 5 choose 8 all over 3. All
That
over
is
3.
exactly right. This is equal to, nice and simple, how many ways can I get 3 heads, 3 choose 8, plus how many ways can I get 4 heads, 4 choose 8, plus how many ways can I get 5 heads, all over the total number of flips I can have. This many have 3 heads, this many have 4 heads, this many have 5 heads. Therefore, this many have 3 or 4 or 5 heads, and this is the total number of ways we can do it. Okay. Another way to think about it is, this is the number of flips that give us what we want, times the probability of each of the individual flips. If that helps you see it better. Is it weird?
Where did the 4 come from?
I don't get your 3 choose 8. Like, why are you saying that?
Thank you. Did I do that up there? Okay. 8 choose 3.
Okay, that makes
8 choose 4.
Like what?
8 choose 5.
There we go.
Okay,
But
sorry.
Why is there 8 choose 4?
So I'm saying I want to know the probability that I have that my number of heads is greater than or equal to 3 and less than or equal to 5. So if my number of heads is greater than or equal to 3 and less than or equal to 5, how many heads can I have? I can have 3 or 4 or 5.
Oh, duh.
This many have 3 heads, this many have 4 heads, this many have 5 heads. This many have 3 or 4 or 5 heads. And the probability of each particular outcome is this, so the probability of all these outcomes is the product. Is there any part of that that's weird? Is the product part here throwing you off? Or was it just counting how many? Huh? No?
It was the 3 choose 8.
It was the 3 choose 8 that was.
Okay.
Yeah, that was
Sorry. So we're good now? Anything weird? Anything you don't like? I know you guys like this stuff. Alright.
Okay.
So now, our next example, we're going to be talking about binomial variables. Now that sounds fancy. What's a binomial variable? It's just one where there's just 2 outcomes. When we're flipping a coin, that's a binomial. We use binomial variable for that. When we, flipping a coin is a good one. So that's the example we're going to use here. So let SB be the sample space for flipping an unfair coin. What does it mean for the coin to be unfair?
That means it's not 50-50.
It's not 50-50. It might be 75% chance I flip a heads and only 25% chance I flip a tails.
This is where you have 1 and then that 1 minus p.
Exactly. So,
How do you get an unfair coin?
how do you get an unfair coin?
Like, how do they, you can't like have an actual unfair coin.
Yeah,
You can have an actual unfair coin.
Like, what do they do to make it unfair?
Well, I'm not sure what they do to make it unfair, but one of the things I can do is make one side of the coin a lot heavier than the other side. So I have it made out of 2 materials. This material is much heavier than this material. That's one way to do it.
So
But I could come up with a really simple way for you to see an unfair coin. I could make it rounded like this, and then flat like that. Okay, there's 2 ways that can land.
But that wouldn't make it fall on the flat side any better.
Maybe more like this.
That's,
One side or the other.
that doesn't.
That's not going to be 50-50.
How do you? It's like a pebble. Okay.
Yeah, a pebble's not going to be 50-50. Go take a pebble and flip it a bunch of times. Mark both sides.
Okay.
Look for a weird looking pebble and try it out.
I know.
But you need them flat enough that it has 2 sides, or you can distinguish 2 sides. Anyways, so we have an unfair coin. So our set of outputs, we'll still just call it heads and tails. But now our probability function's weird. We're going to say the probability of heads is p, and the probability of tails is 1 minus p. Right?
Yeah.
Okay. So, now we're going to create a random variable x. And x is going to be the number of heads in n flips. You with me? It's just how many times heads comes up. We flip the coin n times, however many times heads came up, that's what x is. So let's do an example. Let's say n's 10. How many flips have 3 heads?
10 choose 3.
10 choose 3. Right? There's 10 flips. There's 10 choose 3 ways we can choose 3 of our 10 flips to be heads. What is the probability of getting this particular string?
10 choose 3 over
No.
8.
No, of that exact string. What is the probability that I flip exactly heads and then tails and then tails and then tails and then heads and then tails and then tails and then tails and then tails and then heads?
1 over 2 to the power 10.
It's not a fair coin.
So it's
What's the probability that I flip heads to begin with?
p.
P. Times what's the probability of getting tails?
1 minus
1
p.
minus p.
Rather than writing 1 minus p, I'm going to write q, but same thing, just so I don't have to write 1 minus p over and over again. So times q times q times q. You see the pattern?
Yeah.
Okay, so the probability then is going to be p cubed times 1 minus p to the 7, or 10 minus 3 is the way I'm going to write it. We had 10 flips, 3 of them were p, and 10 minus 3 of them were 1 minus p.
Why don't you just write
Seven.
Yeah, it is 7, but I want you to think about it this way. So that, should have written that up here. Let's just write above it. So it is p times 1 minus p. This one was cubed, this one was 10 minus 3. Okay, so now, if n is equal to 10, what is the probability that x is equal to 3?
10 choose 3 times the probability of what we wrote up there.
X is equal to 3.
Perfect.
why?
10 choose 3 times p cubed times 1 minus p to the 7, or to 10 minus 3.
Can we what?
Let's just move this a little. Probability that x is equal to h now. Let me rewrite this. Why did I use up all my vertical space? So that was the probability that x is equal to what? 3 is equal to 10 choose 3 times p times 1 minus p. This was to the 3, and this was to the 10 minus 3. Okay, so this is how many flips have exactly 3 heads, right?
Mm-hmm.
Yeah.
And this is the probability of getting one of those flips, right?
Okay.
Look, what's the probability of me getting this exact flip? You said it's this number right here.
Yes.
What's the probability of me getting this exact flip or this exact flip where I have H, T, 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 H, T, 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 H, T, and I just switch the order of those last two?
It's the same.
So the probability of getting this was that, the probability of getting this was that. What's the probability that I get this or this?
Let's see. Oh. 10 choose 3 times.
No, just the probability I get this exact flip is some number. We'll call it 1%. The probability that I get this exact flip is some number. We'll also call it 1%. What's the probability that I get this or this? 2%. What did you do? You added them. So you counted how many we were interested in times the probability of each of those. Same thing. This is how many have 3 heads. It's just some number. And this is the probability of each one of those individually. So you're just adding it, this number up this many times. Is that quick?
Yeah.
Yeah. Does that make sense?
Mm-hmm.
Anything weird?
It's looking an awful lot like the binomial theorem.
Yeah, it is looking a lot like the binomial theorem.
Maybe it's just one binomial.
Did I overlook that in the book?
It's the. I don't even know how to explain it.
I guess it was just a no. So I'll quick say no. Okay. Anyways. Alright. So here is the probability that x is equal to 3 if we flip it 10 times, right? Now, what's the probability that x is equal to h if we flip it n times?
So n over h. N choose h.
N choose h.
Times
Wonderful.
p.
N choose times p.
P to that P to the H times
Parentheses.
1 minus P to
You
the
N
N
minus
minus
H.
H.
You see that?
Is that binomial theorem?
It's almost a binomial theorem.
Yeah.
Let's come back over here and write out the binomial theorem so that you can see what that says over there. What was the binomial theorem? The binomial theorem was that
Summation.
if I have p plus q to the n, that is equal to the sum from k equals 0 to n of n choose k times p to the n times q, p to the k, times q to the n minus k. That was a binomial theorem.
Yeah.
Now notice if we make our substitution, so we're calling q 1 minus p, right?
Yeah.
So what is p plus 1 minus p?
1.
1. What's 1 to the n?
1.
1. So when we plug in, we're going to get 1 here is equal to the probability of us getting 0 heads, plus the probability of us getting 1 heads, plus the probability of us getting 2 heads, plus the probability of us getting 3 heads, plus the probability of us getting n heads. So this gives us a probability of all of our outcomes, which we already knew was 1. Do you see what I'm saying?
Oh, which we know is going to be 1.
Which we already know is 1.
Yeah.
Yeah, so plugging into the binomial theorem gives you that the total probability is 1.
Which it should be.
Which it
You're
better
doing
be.
it wrong.
Or you're doing it wrong. That's exactly right. So that's how you can plug it into the binomial theorem. But yeah, so this is just one term in the binomial theorem. You add up all those terms, it's a binomial theorem. You do it when h is 0, then when h is 1, then when h is 2, then when h is 3, all the way up to when h is n. Add those all up, you got the binomial theorem when you plug in p and 1 minus p for your terms. Make sense? Okay. So next, let SP be a sample space, let X and Y be random variables on our sample space. We say that X and Y are independent. No, what am I
What are you
doing?
reading? Go up.
Whoa. Yeah, we skipped a lot.
I'm so confused as a
Okay. Let SP be the sample space for rolling 2 fair dice, and let X1's a random variable that spits out whatever the first die was, X2 is a random variable that spits out whatever the second die was, and X gives us the total rule, or X1 plus X2. Anyone confused? Well, maybe do the note and then we'll go back. So if our particular little s that we're talking about is the rule, one die show the 5 and the other die show the 3, then x1 of that particular rule is 5, x2 of that particular rule is 3, and x of that particular rule is 8. Just make it very explicit. Good?
Yeah.
Okay, so now, first off, let's calculate some probabilities. What's the probability that x is 2?
1.
The probability that x is 2 is what?
1 over 36, sorry.
1 over 36, right?
Yeah.
No.
X is the sum of the 2 dice that you roll.
Oh, yes.
How many ways can we roll a 2?
1 time.
1. You can have the first number be a 1 and the second number be a 1.
Or you can have the first number be a 2 and the second number be a 1.
Yeah, 3 is 2.
Wait. Sorry.
X is the sum of the rolls. Okay, so now let's calculate a different probability. What's the probability that your total roll is 2 if your first die was a 1?
100%.
No, it isn't.
No.
0 isn't.
Wait.
It's
Sorry.
not.
We got 0 and 1.
Sorry, I was reading.
I'll give you a
wrong.
hint,
Isn't
it's
it 1?
between those.
Is 136?
No.
Isn't it 1/6?
1/6.
That's
Wonderful.
what I was thinking.
What?
If you already know that your first die is a 1,
Yeah.
what's the probability that your second die is a 1? It's just the probability that your second die is a 1.
It's 100%.
Yeah, 100% of the time, it'll be 1/6. Every other time, it's not 1/6.
That don't make any sense.
You roll 2 dice.
Okay.
Okay, so secretly, I'm over here and I roll 2 dice.
Okay.
I tried to cover it up. One of my dice accidentally popped out and you saw that it had a 1 on it.
And
Now I
then-
say, what's the probability that overall I rolled a 2?
Oh, I thought you were saying if I totally got 2, what's the probability that I would have a 1 if there's a 1 on
Oh, other way. What's the probability of this given this? So we know this, and we're trying to get the probability of this. Okay. Does that make sense?
Yeah, so it's 1/6. Okay, I understand that.
Okay. So now, what's the answer there?
0.
That's when I was
Oh, okay. 0. There's no chance that you ruled a 2 if one of your if your first die came up a 3, right?
Mm-hmm.
That one makes sense?
Uh-huh.
What's the probability that x, our total rule, is a 2,
Oh,
given that
I
our
see.
first die rolled a 3? Alright, let's try another one.
Okay.
What is the probability that your first die is a 2, given that your second die is a 2?
1/6.
1/6.
Oh, 1/6.
That's not using hands. That's what the point was. So notice that this was equal to, so the probability that your first die was a 2, given that your probability, or given that the second die was a 2, was still equal to, so you're right, this is 1/6. Well, I'll keep the 1/6 there. But this is also equal to just the probability that x1 was equal to 2. Right? The probability that your first die was a 2, given that your second die was a 2, which is 1/6, was just a probability that your first die was a 2.
It doesn't matter.
Wouldn't that be the same as if they were switched?
Yeah, even if you switch them. So this is what we call, this is our example of independent random variables. If knowing information about one tells you nothing about the other, then they're independent. So as a general rule, the probability that x1 spits out A, given that x2 was B, is just the probability that x1 is equal to A.
Yeah.
Another way that we can define it is, let's do it the other way. What's the, because that's what I have down here. What's the probability that x1 is equal to A and x2 is equal to B? Well, that's equal to the probability that x1 is A times the probability that x2 is B. That's another way that you can say that the two variables are independent. So let's do that over here to see it in action, to make sure it makes sense. So we switch this to an and. So what's the probability that my first die is a 2 and my second die is a 2? 1/6 times 1/6, or 1/36.
Yeah.
So since it's equal to the probability of that times the probability of that, then they're independent. That's another way that you can talk about independent variables. And I think the product is what we use down here. And I think it's how we did it for independent events as well. You'll notice that independent random variables and independent events almost one for one line up. Anyway, so let's do the definition. So let SP be a sample space and let x, y be random variables on SP. We say that x and y are independent if for all A, B, then the probability that x is equal to A and y is equal to B is just the probability that x is equal to A times the probability that y is equal to B. In other words, more explicitly, I like it this way better. If x is a random variable from S to some set big A, and y is a random variable from S to some set big B, then they are independent if, for every little a in big A and every little b in big B, then the probability of x being A and y being B is equal to the product of those probabilities. So this is the way I like to think about it, but that's exactly what we did up here. This just makes very explicit where the numbers come from.
Right.
Make sense?
Mm-hmm.
Anything weird? Everything's weird?
Yep.
Just to be 100% sure, the probability of x equaling A and y equaling B is not the same thing as the probability of x equaling A given y equals B.
No, very different, because if they're independent, then the probability that x equals A given y equals B, if they're independent, this is still just a probability that x equals A. Which is not the same thing as probability that x equals A times the probability that
Okay.
y equals B. So yes, very different. Any other questions?
Okay.
Okay. Good? Ready to move the camera?
Yep.
Alrighty. Huh? Okay. So that was random variables. Now we're going to talk about expected values. Give you intuition for an expected value real quick. If I tell you we're playing with 2 fair dice and you roll the dice, what outcome do you expect me to roll when I roll 2 dice?
7.
A 7. That is the expected value when we use a random variable that spits out the sum of the 2 dice. Then its expected value is 7. So that's an example of expected value. So that's your intuition for what it is. What it is a weighted average, but we'll go over explicitly what it is here. So it has to be a real random variable. So let x be a real random variable on some sample space SP. Then the expected value of x, which we write e of x like that, is equal to the sum for all little s and big S of what x assigned to that s times the probability of that s.
Those are little s's?
Uh-huh.
Okay.
For every little s and big S. So expected value is a sum of weighted numbers. We take their outcomes and we weight them by the probability, is one way to think about it. So we'll get to rolling 2 dice in a second to show that 7, but let's start out with a simpler case. Let SP be a sample space for rolling a fair die, and let X be the number rolled, okay? So we're just rolling 1 die for now. What do we know the expected value on 1 die should be?
7.
On 1 die.
Oh, sorry.
2.
There isn't.
3.
It's 1 6, right?
6. Oh, what? What is
Oh,
question?
Holy cow. So 7, no problem, but 1 die. Okay, that's strange. If I were to roll 1 die a ton of times and then average out the rolls, what would the average be?
6.
No, it would be.
6 is the highest number I can roll. On average, I'm going to roll a 6.
3.
3.5.
No, yeah.
3.5. Okay.
Why is 3.5? What?
What? I am going to roll a 1 just as often as I'm going to roll a 6. I'm going to roll a 2 just as often as I'm going to roll a 4. I'm going to roll
You
a...
missed 5, bro.
Thank you. And I'm going to roll a 3 just as often as I'm going to roll a 4.
Yeah.
Right?
Yeah.
So it's 3, 4.
So, what's the best way to make you see this? Here's how I make you see this. So let's say I roll the dice a ton of times, we'll call it n times. N is the number of times I'm going to roll this dice. It's going to be like 100. I am going to get 1/6 of the time, or n over 6 times, right? Plus, I'm going to get 2 n over 6 times, plus 3, I'm going to get 3 n over 6 times, plus I'm going to get 4 n over 6 times, plus I'm going to get 5 n over 6 times, why do I keep doing that? Plus 5 n over 6 times, and then I'm going to get 6 n over 6 times, right?
Yeah.
You good with that?
Yeah.
Okay, so now, that's how many times I'm going to get it. If I'm going to average it, I need to divide it by how many times I've rolled. That gives me my average roll. Divided by n. You good with that? We're looking for my average roll.
Wow.
Yes.
Okay, so let's do the math. So we have 1/6 plus 2/6 plus 3/6 plus 4/6 plus 5/6 plus 6/6. What's that going to come out to?
That's a really good question.
Well, it's 1 plus 2 plus 3 plus 4 plus 5 plus 6.
21.
21. How'd you do that?
I added them.
7 plus 7 plus 7. Right? So we've got 21/6 over n,
That's
or 21 over 6n. You good with that?
Yeah.
Cancel out 3 top and bottom. You're left with 7 over 2n. Oh, the n's cancel out because we also have n's up there. Sorry. N's go out. Factor out an m from the numerator. That cancels out with the denominator. Right?
Yeah.
Yeah. So, I'm left with 21 over 6, or 7/2, or 3.5. Make sense?
Yeah.
There's another way to make it appeal to your intuition.
Hey, what did you
What's
just
the average of
tell
1
me?
and 6?
3.5.
What's the average of 2 and 5? What's the average of 3 and 4?
So that's,
You're saying this is EX?
I don't see.
Well,
that.
EX is going to give you this. I'm trying to give you intuition.
He's just trying to
for
tell us how to average.
how to think about expected value intuitively. It's
Okay, but
the average value you expect to get if you do something a whole bunch of times.
you can't get a 3.5.
You can't get a 3.5. That's correct.
That's the expected value.
It's the expected value, not the most likely outcome. Right?
What you expect from us.
Here's one way to think about it. Maybe this will help filter your intuition. Let's say I'm going to play a game,
What do you think?
and the game is whenever you roll the die, whatever number you roll, I have to give you that much money. If you roll 1, I give you $1. If you roll 6, I give you $6. Okay? But we want the game to be fair. How much should I charge so that you can play the game?
Oh, this is where you came up with your 3.5 yesterday.
We talked about this yesterday.
Oh,
Yeah.
yeah, that's the expected value of rolling 1 die, 3.5.
What was yesterday?
It was a good day. You'll never know.
Oh, sorry.
So $3.50 is what you'd have to charge to keep it fair. If you want to make money in the long run, you need to charge more than $3.50.
Why would you?
I see.
Does that make sense? You have to charge $3.50 for it to be fair? What do you think you should have to charge for it to be fair? What makes sense to your brain?
$5.
$5. Obviously, you make money on that. Because I have to roll a 6 to make money. If I roll a 5, we come out even.
Okay, wait. So you're saying you can pick a number and however many times you roll that, then I'll give you $1.
No, I'm saying I made up a game where you roll a die, and whatever number you roll, I have to give you that much money in dollars. So if you roll 6, I have to give you $6, but if you roll 1, I only have to give you $1. Question: how much should I charge for you to be able to get a chance to roll the die so that it's fair? So in the long run, I don't lose or make any money.
Okay, yeah.
$3.50.
Except for you could start it then.
I might happen to make money, but I might happen to lose money. But $3.50 in the long run should come out right even.
Yeah, okay, that makes sense.
Make sense? Okay, so that's what the intuition of what expected value is supposed to capture. But let's just calculate expected value. We're going to do the exact same calculation that I'm erasing, basically, except for without the ends. So, the expected value of an outcome on a die is equal to the sum for all little s and big S of this product. So, we'll start with 1. What is S in this case? S is the set 1, 2, 3, 4, 5, 6, right?
Yeah.
Yeah.
What is x of 1? 1. Times, what's the probability of 1?
1, 6,
1/6. Plus, what's x of 2?
2,
2. What's the probability of 2?
2, 6, 1,
1/6. Plus 3 times 1/6 plus 4 times 1/6. Get to the point where I'm 4, 6. Hard to get my hand to just do the
Basically
1,
what
6.
it is.
I know, that's why my hand wants to do it so bad. Okay. So, that is equal to what? What's 1 plus 2 plus 3 plus 4 plus 5 plus 6?
21 over 6.
Woo!
Oh,
21 over 6, which is 3.5.
wait, why is that 21?
What's 1 plus 2 plus 3 plus 4 plus 5 plus 6?
Well, it's 21.
Okay, and each of those are times by 6. So factor out the 1/6, or
Oh.
multiply by 1/6 when you're done, or however you want to think about it. Make sense?
Yeah.
Anything weird?
So you're basically just trying to find the average of
It is a weighted average. It's just the average when it's a fair, when you have a fair die. When all the outcomes are equally likely, it's just an average.
So we
If
could,
the outcomes aren't equally likely, it's a weighted average.
so we could just find the average instead of doing the
Like, do you know how to calculate your grades? If I told you how many points you got in the homework category and how many in the test category, do you ever do that? You never do that?
Just look at it.
Wow.
Do you do that, Ronnie?
I did that all the time. I set up to figure out what exactly I needed to get on my assignments based off of where I was to maintain a grade that I wanted to maintain.
Trying to calculate the minimum that you have to get on your homework test.
Yep. Especially when it came to my final.
Well,
I
I
need
guess
to
I
know
had
the
to do
very
that.
minimum score I need to get on my final.
Yeah.
That's
It's past the
what Robert
class.
did.
Yeah. Me and Laura sometimes do that.
But do you just go play on the computer, plug in one number, and keep plugging in until it gets the number you want? Or do you actually calculate it?
I actually did it when I was turning in my homework. I was like,
So what you did, if you know how to calculate your grade, is a weighted average. That's the hardest expected value gets in this class almost. Is calculating the homework grade. Anyways, let's go back to our spinner. We love our spinner, right?
Mm-hmm.
So we've got this spinner, and now the question is, if I let x be the number you spun, makes perfect sense, what's the expected value of x? So we're going to go through 1, 2, 3, 4, 5, or 1, 2, 3, and 4 and plug it into here. So this is equal to, what's x of 1?
1.
1 times what's the probability of 1?
1.
Plus what's x of 2?
2.
Times the probability of 2?
1.
Plus
3
3.
times 1.
And 4 times 1.
And so, what's that equal to?
And over. And over.
I don't know, 3 plus this. 1 7/8.
That's why I got 2. Anyone else get something different?
No,
Oh,
that's
wow.
I
exactly
don't know
what
how
I
to
got.
do that.
What'd you get?
Yeah, just 1 and 7/8.
1 7/8.
Yeah, 15 over 8.
15 over 8. Yep, that's what I got. Okay, 15 over 8. Notice 15 over 8 is just under 2. What is that?
What's
1
2?
point, is it 8? 7, 5?
Like, well,
Yeah, I think that's right. So, if you wanted to make a game where people come and they get to spin the spinner, and you give them $1 if they spin this, $2 if they spin this, 3 if they spin that, 4 if they spin that. If you charge them more than $1.875 to play the game, you'll slowly make money.
just charge them $2 to play.
You have to charge them more than 1.87.
That's what he said.
Right.
Oh, I thought you said this. Okay.
So if you charge them $1.88, oh, you'll make it big.
Charge $2.
Yeah,
Because it kind of seems like it's in the middle.
yeah, like they'll think it's in the middle.
Yeah. Yeah, you could probably get away with charging $2. I don't know. Try it on your classmates.
Alright.
Hey guys, wanna play a game?
We could actually do it.
Okay.
We should.
So now let's calculate the expected value. So we're rolling 2 fair dice. X is the sum of the dice. Okay, so what's the expected value of X?
7.
Oh, be 7.
It's going to be 7, but how do we calculate that?
Transformation.
Yep, so we got to sum up for all little s in
And
big
big
S of X of that S times the probability of that S. How many terms am I going to have when I write this thing out?
36.
36 terms.
Wait,
Oh,
why?
yeah.
Yeah.
That's too many.
Yes. So this is equal to x of what we get when we plug in 1, 1 times the probability of 1, 1 plus x of what we get when we plug in
Well, you
1, 2 times the probability that we roll a 1, 2. And this is going to be a nightmare to write it all out, right?
Yes.
Plus x of our last one that we'll do is 6, 6 times the probability of 6, 6. So if you're ever stuck on how to calculate one of these, you can always just grab the bull by the horns, do it all, add it all up, all 36 terms. It's a nightmare, but you know how to do it, right? And you can calculate that. Well, we're not going to deal with that nightmare. So we're going to come back and do a quick theorem, then come back and finish this.
Okay.
Okay. Huh?
She said why, and then she said okay.
Why does this have 36 terms?
I don't know why we theorem. Let's just do it.
Well, how would you calculate this otherwise?
I don't know, 7.
It's 7. Alright, we'll prove the theorem. So if S and P is a sample space, and X is a real random variable, then the expected value of X can also be calculated this way. You sum up for every possible real number, that real number times the probability that X is that real number. Maybe we'll just state the theorem, come back up here and use it, and then prove the theorem. That way you can see it in action before we use it. So let's see this in action. So what we're saying then is this is also equal to, I can just do
That was disgusting.
equal to, what are all the possible real numbers that I'm going to get out of my x of s function?
36.
2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12.
Yeah.
That's it,
Just kidding.
right? So I can rewrite this. This is saying I can rewrite this as a sum for every real number times the probability that I get that real number. Now notice for numbers that aren't up here, numbers that aren't 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, or 12, their probability is 0. So most of the time we're just doing 0 times
Oh, it's just 1.
the number.
Just kidding. It's 0.
What's the probability that I roll 2
I
dice
asked
and I get a negative 54?
1, apparently.
0. So the only real numbers that have probabilities that aren't 0
Oh, okay.
is just 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, and 12.
Yes.
So this sum for all real numbers, we do that real number times its probability. Most of the times the probability of an A is 0. It's only for A's that come out of our x of s that we have actual probabilities.
Yeah.
Okay. So all we need to do is do it for the real numbers where we actually get values. So we actually get values at 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. So it's going to be the real number 2 times the probability that x is equal to 2 plus the real number 3 times the probability that x is equal to 3 plus ... plus the real number 12 times the probability that x is equal to 12. Right?
Yeah.
So this is equal to, and now let's do it, let's actually calculate it all out now. So what's the probability that I get a 2?
1.
1 over 36 times 2 gives me 2 over 36, right?
Mm-hmm.
So 2 over 36 plus, what's the probability I roll a 3?
2 over 36.
2 over 36 times 3 is
6 over 36.
6 over 36. We'll keep it in terms of 36 so that it comes out nicer. And then what's the probability of rolling a 4?
3 over 36.
Times 4?
12 over 36.
What's the probability of rolling a, let's see, this was 2, 3, 4. What's the probability of a 5?
4 over 36.
4 over 36 times
20 over 36.
How are you guys
20
getting
over
that?
36.
Can I please get in on the secret?
Okay. This one's just for Rhoda. So let's see, this was 1, 2, 3, 4. Now we need to do 5. What's the probability when I roll 2 dice that I roll a 5? Wait, this was 2, 3, 4, 5. We already did 5. Okay.
Yeah.
I was going to say, isn't that what we just did? This was 2, 3, 4, 5. Okay. What's the probability that I roll a 6?
1.
There's a 100% chance I'm going to roll a 6.
136.
With
136. I have 2 dice.
Oh.
How many ways can I get a 6? 4 plus your favorite number.
4 plus 1.
Your favorite number.
What is my favorite number? 1. Oh. How's it 5?
You can get, let's see, a 5 and a 1, a 4 and a 2, a 3 and
Hey,
a
but
3,
how do
a
they
2
know
and a
that
4.
so fast?
They're counting because it increments.
Because God
So,
showed us a trick
Yeah,
last week.
we have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. How many ways can I roll a 2? 1.
One.
How many ways can I get a 3? 2. 4, 3, 5, 4, 6, 5, 7, 6, 8, 5, 4, 3, 2, 1. They count up and down.
Okay. So for some reason I was thinking that the 4 lined up with the 6.
So now we're doing, how many ways can we roll a 6? 5 over 36. Oh, sorry, there's 5 ways we can roll a 6. So what's the odds of rolling a 6?
5 over 36.
Times,
Times.
and now times that by 6.
Okay. I don't know how I times it by 6, but.
It's
What's
30
5
over
times
36.
6?
Okay, 30.
30 over 36. Okay. Next, so that was a 6, right?
Mm-hmm.
So now we're doing a 7. What's the probability that I roll 7?
6 over 36?
6 over 36 times 7?
42 over 36?
42 over 36, right?
This is gonna be way big.
Plus, how many ways can I roll, or what's the probability I roll an 8
5 over 36?
times 8?
40 over 36?
Wait, it's going back down. Oh.
Plus, let's see, are we on now? 9? What's the probability I roll 9
4 over 36?
times 9?
36 over 36?
Okay, but they're not matching up, and you're saying that they're the same now.
Well, now we're calculating this. We're doing 2 times the probability of 2,
Oh, yeah.
plus 3 times the probability of 3, plus 4 times the probability of 4, etc.
Okay, that.
All the way to 12 times the probability of 12. What one were we on? 10?
30 over 36.
That's 30 over 36. And 11 is
22 over 36?
22 over 36. And 12 is,
Over 36?
and that's equal to, now just add those up in your head real quick.
7?
Oh, yeah.
7.
Good job on that.
So, should probably be able to figure that out really quick. Here's 1. Here's 2. 22 plus 12 is 34 plus 2 is 36. So there's 3. Let's see, any obvious ways to do it from here? Maybe now it's easiest to just add. So we've got,
Double.
huh? I
Try to
can
do
just add.
52.
82 plus 30 is 112, 132, 144.
Well, see, wait, 52, so you do 42 and 12. Oh, no, you can't. Never mind.
You just listen to Emma.
Well, 144 divided by 36 gives us 3.
144 divided by 36?
No,
No, because it's
4.
54?
4?
Yes. We already have.
Oh, 4, yes.
Yeah, you're right.
36, 3 times 12. 12 divided by 3 gives 4. So yes, this gives us 4, so we better have only counted 3 before that.
We only counted 3.
Okay, perfect. which comes out 7. Okay, so that is using this theorem. Now let's prove this theorem. You ready to prove the theorem?
Yes.
Okay. Let SP be a sample space and let X be some real random variable. We're calculating the expected value of X. We're showing that's equal to this. By definition, the expected value of X is equal to this, right? Okay. So now, all I'm doing, remember that this is just a big sum. This right here is just a massive sum. And it doesn't matter what order I add those things together in, right?
Yeah.
So I'm saying right here, I'm saying for each real number A, group all the terms together where X of S happen to give me that A. So when A is 1, group all the ones where X of S was equal to 1, and add those first. Then all the ones where A is equal to 2. Then all the ones where A is equal to 3. So we're still summing all the exact terms that we were adding before. We're just grouping them together in this internal sum by the ones that give me the same A here for my X of S.
Okay.
For example, we would be grouping the rule 1, 2 with the rule 2, 1, because those both spit out a 3. So this is just an internal grouping in this sum. Does that make sense what I'm doing here?
Yeah.
So each of these, I'm grouping all the terms together where each X of S gives me a particular A. So when A is 1, this is the sum of all the things where X of S was 1. When A is 2, then we sum up all the things where X of S was equal to 2. And you do that for every real number, you got all the terms. Most of the times, there's not going to be any terms that give us a particular A, right? If I pick A equal to negative 97, then we don't have any internal sum there. Does that make sense what I'm doing?
Yeah.
For every one of these terms, X of S has to be some real number. We're grouping all the ones that spit out the same real number together. That's all we're doing. Am I overstating this?
Yeah.
Okay. So if that makes sense, then since all the X of S's inside of this sum are just A, I'm just doing a substitution replacing with A. For every real number, we're adding up all the terms in S that spat out an A in this position. That makes sense?
Yep.
Okay? Now since I have a sum, I'm summing up terms where I keep using A times something, A times something, A times something, I can factor the A out of the sum.
Yeah.
So now, should have made a side note of this. This is what I meant to do over there. The probability that X is equal to A is by definition the sum for all little s in S where X of S is equal to A. That is of the probabilities of those S's. The probability that X is a particular outcome is equal to the sum of all the probabilities where X of S was A. Right? Sum of all the probabilities where X of S is A, and that's what we mean by the probability that X is A. Right? When I say what's the probability that X, when we're thinking about rolling two dice, when I say what's the probability that your rule is equal to 3, you said that's equal to the sum of all the outcomes that gave me a 3 in X of S. So that's equal to, well, there's two of them, right? That's equal to the probability of 1, 3, plus the probability, no, of 1, 2, and 2, 1, plus the probability of 2, 1, and that's how you calculate this probability, which is equal to, in this case, it would be 236, right? So when I say what's the probability that X is 3 when we were rolling two dice and X is the sum of the dice, that's the probabilities of all the outcomes that gave me a 3. That's exactly what this is saying. And notice that that is exactly what we have right here now. So this is exactly the probability that X is equal to A. So now we have the sum over all real numbers of A times the probability that X is equal to A, which is what we were after. Kind of dense in notation, but overall what's happening is actually kind of simple. We just have a bunch of sums, We group certain terms together based off them having the same coefficient, factor out the coefficient, relabel the remaining sum, that thing. I don't know, good? Bad?
So,
Strongly recommend reading this section, by the way. I know I already said that, but
I read
just a
that
crazy idea. Huh?
one. I had that one.
That's good. Now you can read this one. Okay. So, let's calculate some more probabilities. Never get tired of this, right?
Never.
That's the spirit. Okay. Back to looking at our spinner down here. From the spinner, make a game where players receive $10 for spinning an odd and $20 for spinning an even. And let X be the payout. In other words, X assigns 10 to 1 and 20 to 2, 10 to 3, and 20 to 4. Right?
okay.
So, what is the expected value of this game? How do we go about calculating this?
So there's gonna be
What are all the possible values X can take?
1, 2,
1,
3,
2,
4.
3, 4.
Sorry. What are all the possible values X can be? X can spit out.
10 and 20.
10 and 20, right?
Mhm.
X of S can be 10 or X of S can be 20. Right? So this is going to be equal to 10 times the probability that X is equal to 10 plus 20 times the probability that X is equal to 20. Follow that?
No.
Yeah.
No?
What do you mean X is equal to 10?
X
What
is
is
my random variable.
So
If you
what-
spin a 1, X spits out 10. X gives you how much money you win,
Yeah.
right? If you spin a 1, X spits out 10.
So why wouldn't it just be 10 times the probability of X equal to 1?
You are now calculating it this way,
Mm-hmm.
right? So you want to do 10 times the probability that X isn't the number that we output, so you can't say X is equal to 1. But you want to come up with another random variable. You want Y to be your spin. Y equals your spin. So now Y is 1, 2, 3, 4.
Just like we had down there. He wants to do what we did down there.
And even if you do it that way, how do you get assign your dollar values after? You're kind of wanting to do a hybrid of the two. You're just wanting to say, I get $10 if I spin a 1, I get $20 if I spin a 2, I get $10 if I spin a 3, and I get $20 if I spin a 4.
Isn't that what you're saying?
No, you can't do it that way. So that is doing it this way, actually. Okay, that is doing it this way. So you want to do 10 times 1/2 plus 20 times 1/4 plus 10 times 1/8 plus 20 times 1/8, right? That's how you want to do it?
Yeah.
Okay, now look what we're doing here. 10 times the probability that X is a 10. What's the probability that X was a 10? When do I get a 10? I get a 10 when we spin a 1 or a 3.
So 5 out of 8?
5/8. So this is equal to 10 times 5/8 plus 20 times, what's the probability that I get a 20?
3 8.
3/8.
Okay, now I see what's going on.
Either way, you get the exact same numbers.
Yeah.
One's just using this theorem, the other one's using the definition directly. Both work. So whatever appeals to your intuition more. Alright. Let's calculate some more probabilities. Let SP be the sample space for rolling a fair die, and let X be the absolute value of the difference of the dice. So in other words, if I roll a 6 and a 3, what's the absolute value of their difference?
3.
3. I roll a 5 and a 5, what's the absolute value of their difference?
0.
Mm-hmm.
0. It's just the difference between the two die.
Yeah.
Okay.
Okay, so that's our expected value. Or sorry, that's our random variable. Let's calculate some probabilities. What's the probability that we get a 0? There's 6 of them, so what's the probability?
0. 1.
1/6.
1/6, or 6 over 36.
Yeah.
6 out of our 36 rules, the difference in the absolute values are 0. Namely 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, 6, 6. Those are the 6 rules where the difference between the two dice is 0. Make sense? Okay. How many ways can the difference be 1?
1, 2, 2, 3, 6.
6 ways?
5 ways.
5?
Am I getting the right number?
6.
We got 6 and 5. We got 5 and 6.
10.
10? Any other answers?
I'll say 11. I'll top them off.
I'm going to say 11. What's the one you're counting? She's not. So let's look at it one way. I can roll a 1 and a 2, a 2 and a 3, a 3 and a 4, a 4 and a 5, a 5 and a 6,
Then the other way.
and then the other way. I could have rolled a 2 and a 1, a 3 and a 2, so it comes out 10
Peter was wrong.
out of 36.
That's too bad.
Emma was right. The rest were wrong. No answer is a wrong answer.
You just said
You only get partial credit if you leave a blank.
Okay.
What?
You just said the rest were wrong, and then you said no were wrong.
No answer is a, oh. No answer, as in not answering, is still a wrong answer. No answer is a wrong answer. Not there are no wrong answers. Yes, there are many wrong answers and few right answers. And no answer is a wrong
So
answer.
everyone was wrong but Emma.
Yes.
Okay.
Okay. What's the probability that their difference is 2?
4, 2, 5, 3,
Quite a bit.
You think
1,
it's that big?
3,
1,
3,
2,
5.
4, 1. Wait.
You'll see the
12?
pattern eventually.
12.
Time to go up.
It goes higher.
What?
6.
I got 10 again.
You can roll a 1 and a 3, a 2 and a 4, a 3 and a 5, a 4 and a 6, and reverse.
8.
Oh.
That was my next guess.
Okay, now without counting, what's the probability for 3?
6.
6 over 36. Good job.
What?
And what's the probability for 4?
10 over 36.
You just got fired.
I should have started.
4 over 36.
Ow.
2 over 36.
Where's your pattern?
0 over 36.
10, 8, 6, 4, 2.
12, 10, 8, 6, 4, 2, 0.
12.
12.
12, if we could reverse them, it would have been 12. Uh-huh.
Darn it all.
There's 6 ways to count up, but we couldn't count down. There was 5 ways to count up and down, 4 ways to count up and down, 3 ways to count up and down, 2 ways to count up and down, 1 way to count up and down.
Here,
We're
ways.
done.
Oh.
That makes sense.
And no ways to count up and down on 6, huh?
I'm confused.
You'd be counting the same one twice. Because 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6 are the same thing as 1, 1, 2, 2, 3, 3, 4, 4, 5, 5, and 6, 6.
Are you saying
You
the
can't
Mine
minus
about X
anything
equals
and
6.
get minus anything.
Oh, sorry, here I said 0.
You can't minus anything from anything and get 6.
Oh.
I can't ever have it, I can't roll 2 6-sided die and have their difference be 6. The highest I can get is 5, and that's when I roll 1 and a 6 or a 6 and a 1. Was there any other questions or things I said wrong?
I'm confused. Is the probability of x equaling 0 6 over 36 or 12 over 36? Because you said
It's 6 over 36. I'm saying the pattern is to think about
He was just
up and down. But this one you can't go back down. All the other ones you can. That's just how I thought about it. Everyone has their own tricks. Right, Laura? Agreed. That's a big smile. Alright.
take a block.
Let's make sure that we didn't make a mistake though. Better add up to 1. So we got 10, 20, 36. Okay, we're good. So now the expected value of x.
Okay, so we do,
It's gonna be 10 over 36 plus 16 over 36 plus, I think I'm doing this wrong.
You're doing it
10
right.
over 36
Plus 18 over
plus
36,
16 over 36
plus 8 over 36, plus 10 over 36. That's how you were thinking.
plus 8 over, is
yeah,
that 16?
then 18 over 36.
Oh, 16, yeah.
What?
And then it's 10 over 36.
So-
But you times it, right? By
This is equal to 0 times the probability that x is equal to 0, plus 1 times the probability that x is equal to 1, plus 2 times the probability that x is equal to 2, plus 3 times the probability that x is equal to 3, plus 4 times the probability that x is equal to 4, 4, not 5, plus 5 times the probability that x is equal to 5. Right? So that's going to be, here we get 0 plus, what's this one?
10 over 36.
10 over 36. Plus, what's this one?
16 over 36.
16 over 36. All right, Rhoda, what's the next one?
18 over 36.
Good job.
I bet Laura can't do that one.
All right, Laura, what's the next one?
19.
I don't even know what you guys are doing, honestly.
Okay.
Why did you say so?
What's the this is a 4, by the way. What's the probability that x is 4? Where did we lose you? Did we lose you at what x is?
Yes.
Okay. X is the absolute value of the difference in two die. Or in other words, if you don't want to think about the absolute value, it's what you would tell me if I said, what was the difference between the two die? So I roll two 6-sided die. I roll a 5 and a 3. What's the difference between those die?
2.
2. That's it. I roll a 6 and a 1. What's the difference between those die?
5.
5. So now you're getting it. So when I say, how many ways can x be 0, means how many dice rolls are there where there's no difference in what I rolled? There's 6. I could have rolled a 1 and a 1, or a 2 and a 2, or a 3 and a 3, or a 4 and a 4, or a 5 and a 5, or a 6 and a 6. So there's 36 possible rules. 6 of those are where the first and second die show the exact same thing. That would make sense? So now let's look at this one. What's the probability that their difference is 1? How many rolls have a difference of 1? I could have rolled 1 and a 2, right? 2 and a 3, 3 and a 4,
Yeah, I see.
4 and a 5, 5 and a 6, and then 6 and a 5, 5 and a 4, 3 and a 2. I skipped one. 2 and a 1. I skipped one. Either way, there's 10 of them, right?
Yeah, that makes sense.
Okay, and 8 ways that you get a difference of 2, 6 ways that you get a difference of 3, 4 ways that you get a difference of 4, 2 ways that you get a difference of 5, and you can't ever get a difference of 6. I can't roll two 6-sided dice and have their difference be 6. The biggest it can be is 5. Right? My most extreme values are 1 and 6. That difference is 5. Good? Okay, so now we're just plugging in to this formula right here. I'm going to do all my possible outcomes, all the real numbers that I can get to spit out of this function, x. What are all the possible numbers I can get out of there? 0, 1, 2, 3, 4, and 5. So I'm going to do 0 times the probability that I can get a 0, plus 1 times the probability that I can get a 1, plus 2 times the probability I can get a 2, etc. So this number 0 is 0 times 6 over 36. This number 10 over 36 is 1 times 10 over 36. This number 16 over 36 is 2 times 8 over 36. This number 18 over 36 is 3 times 6 over 36. And now back to your question. What's this one?
8 over 36.
Almost.
No, 16 over 36.
16 over 36. There we go. All right. Peter,
10 over 36.
10 over 36. Anyone disagree with that?
That's too bad.
Now, what is the total sum? We have 10, 26. Oh, that's an ugly number. Let's see, 10, 26, 36. So we have 1 and 34. 34 over 36.
Yeah.
So that's going to be like a 1.94-ish, somewhere around there. I bet the book has it. Scroll back up. No, it's probably with 2 dice. We did that, we did that. Where is this example? Oh, oh, geez, this is a big section.
Are we at the end of it?
No, I keep scrolling up higher and higher in it, trying to find where we are. 1.944.
You were so close, Donnie.
So close. Alright, so we'll do one more proof and then we'll call it for today. And this proof is stupid easy proof, but we'll do it anyways. Proof that the expected value of x plus y is equal to the expected value of x plus the expected value of y. With me?
Yeah.
Okay, so what is the expected value of x plus y?
It's the sum.
Just
S
right from
S.
definition, it's a sum from all little s and big S of what you get when you plug in
X of
s into it
Plus y of s.
times the probability of s, right?
Yeah.
That's it by definition.
Yep.
And this is equal to, I can distribute that ps to each of those terms. So that's equal to the sum, it's always the sum for all little s and big S, of x of s times p of s plus y of s times p of s. You good with that?
Yep.
Okay? And there's no reason I can't split this into 2 sums.
Yeah.
So that's equal to the
Yes.
sum of the x of s times p of s. And now we're stopping, so maybe put parentheses here. Up here we're saying we're summing up the whole thing. Now we're saying the sum from there to there plus the sum of all the y(s) times ps, which is exactly equal to the expected value of x plus the expected value of y. Right?
Yeah.
Easy as pie?
Mm-hmm.
Alright, so we'll call it there. Get started with your homework on this section. We'll finish this section next time. Read this section now. This stuff is kind of dense and we're probably only like a third the way through it. So I'm going to need to do a few more proofs. So maybe start on your homework on this section the best you can to get comfortable with these things. I need you guys to, when you look at that thing, to be comfortable as just viewing that thing as a sum of terms, a sum of products. Like, we got to get to the point where that's just easy in your head. Otherwise, you're going to get lost in the proofs that we're doing from here on out. Maybe go back and reread this proof a couple times until it clicks. Because I think if you're okay shifting around terms in a proof like this, you might be okay with how we go from here. But we're going to need to do stuff like this. So stare at it until it makes sense. Read, the author gives tons of notes as he lays this out. He doesn't just lay it out like I do. What's up?
So we're just gonna do our homework to the point of what we know, and then stop and come to class next week and ask you questions about the rest of them?
Yeah, just struggle with it the best you can to try and
Okay.
start getting in your brain what exactly these expected values are. Anything with variance, just ignore if it says find a variance, unless you want to look at the definition. Just actually read your textbooks and learn stuff on your own. I know, crazy world. I hear some people do it though.
Weird.
Weird.
Have you ever tried to do that?
Every class I've taught, I started up, well, with the exception of a couple,